Welcome back, students, to our third module on chemistry. This will be module 1.2.3, chemical bonds. Last time we ended with introducing you to the periodic table of elements, which you see here. We can put that on slideshow for you like that. Today's module is going to concentrate upon chemical bonds. And it is a fact of chemistry that most atoms do not exist as individual atoms, but rather they form chemical bonds in which they bond together and form molecules. Chemical bonding is a matter of energy and of stability. The electrons in the valence shells interact and form a more stable configuration. Varying elements differ in their reactivity or stability, and this is again according to their valence electrons, the number of electrons that are present in the outer shell. As an example, helium has 2 electrons in its first shell, and the first shell can only hold 2. Therefore, helium is very stable, very content, and it is not involved in other chemical reactions. On the other hand, we can compare this to the behavior of hydrogen that has a single electron in its first shell, yet the first shell holds 2, and this leads hydrogen to be unstable and to cause it to be involved in many chemical reactions. You will recall the first shell holds 2 electrons, the second shell holds 8 electrons, the third shell holds 18 electrons. There are, in fact, 3 basic types of chemical bonds: ionic bonds, covalent bonds, and hydrogen bonds, and we'll discuss each of them in turn. First, ionic bonds, and the name of the bond type actually helps to describe it. Of course, ionic refers to ions, and you will recall that an ion is a charged atom that has either more electrons and protons or fewer electrons and protons. The fact of the matter is about ionic bonds is that they have a fairly weak bond strength. As a consequence, they are relatively, that is, ionic bonds are relatively unimportant in living things. On the other hand, ions are very common in living things, but because life occurs in solution, it causes it prevents the formation of ionic bonds. If we look here at the example, this is showing the formation of common table salts, sodium chloride. And so we see a sodium atom and a chlorine atom. And you'll notice that sodium has only a single electron in its third shell, which can hold 18. This makes it very unstable, and so it very readily will donate that. Chlorine has 7 electrons in its third shell, and you will recall that although the third shell holds 18, there is a stable point at 8, and so it will readily accept an electron, giving it 8, and both would then be stable, relatively stable ions, but they would have opposite charge, and positive and negative attracts, and this attraction is in fact the ionic bond. Here we can see a little cartoon, shows the little blue sodium and the green chlorine, and the green chlorine is saying, I only have 17 electrons, I'd feel so much better if I had one more. The blue sodium says, I have an extra one, here, you can take it. The chlorine says, wow, are you sure? And the sodium says, yes, I'm positive, RDRR. Here in many ionic compounds form a crystal lattice. And if you could look very closely at table salt, you'll see that it has little square crystals. And this is because the sodium and the chlorine ions are so tightly packed in this regular pattern. But once again, these kind of bonds just don't work well in living things because they are in solution. So let's look at a second type of bond, covalent bonds. And once again, there's a lot of information in the name of the bond. Covalent means co means together or shared, and valent means refers to valence. So shared valence bonds. Covalent bonds are bonds that involve the sharing of electrons. And covalent bonds are bonds that have high bond strength. And these are the types of bonds, covalent bonds, that biological molecules are primarily formed by. We see a couple of simplistic examples down here. Here it shows 2 hydrogen atoms, recall that each has a single electron in its first shell, and the first shell can only hold two. And so that by sharing those two electrons, it actually satisfies the requirements of both. Now, while this works for chemistry, it doesn't work for accounting. You can't use the same money to satisfy two account holders, for example. But in physics, it provides the sufficient stability to allow a stable point. So covalent bonds work in chemistry. I often think of this as jugglers, and they're sharing balls and they juggle. If you've ever seen a juggling act, they can do this. And so it can satisfy both of them. And as I say, that doesn't work, however, with money. So those of you in business and finance, take note. Okay. There are, in fact, two different types of covalent bonds. The first that we're going to discuss is a polar covalent bond. And again, the name is important. The word polar says that the molecule has poles. As a magnet, has a positive and a negative pole. In a polar covalent bond, the electrons are unequally shared, and they spend more time with one atom than another. The atom which the electrons spend more time with is said to be more electronegative. Electronegativity is an inherent attraction for electrons that an atom has. And if the electrons spend more time with one atom than the other, and remember electrons have a negative charge, it will give the one atom where they spend more time a partial negative charge, and because they're not spending as much time with the other atom, they'll give the other end of the molecule, where the less electronegative atom is, a partial positive charge. And so the molecule is now polar. It has a negative and a positive end. And so that's a polar covalent bond caused by unequal sharing of the electrons. The second possibility with regard to a covalent bond is that the electrons are shared evenly. And the name given to the type of covalent bond formed when this happens is called a non-polar covalent bond. So once again, that simply means the electrons are equally shared. They spend an equal amount of time with both of the atoms involved in the covalent bond, and therefore neither has a partial charge. There are no positive and negative poles formed. Here is an illustration of a water molecule showing the structural formula, showing the oxygen, which is a very electronegative atom, and the electrons spend more time there than with the hydrogen. And so the oxygen will get a partial negative and the hydrogen will get a partial positive. And it's one of those interesting phenomena. And this has great implications for life and for biochemistry. So it's very critical that you understand what a polar covalent bond is. The third type of bond is in fact related to a polar covalent bond. A hydrogen bond is the third type of bond. And this bond is simply a weak attraction between two molecules with polar covalent bonds. Hydrogen bonds have fairly low bond strength, but they are so numerous that they can exert an important overall force. So hydrogen bonds are pretty important. And as you can see down here on the bottom, this shows two water molecules, H2O. The O is the red atom and the white circles are the hydrogens. And this little dotted line here is a weak attraction between the negatively charged oxygen and the positively charged hydrogen. And notice this shows it forming and breaking, and that's really what happens. So again, although the bond strength is very low, they are very numerous and therefore they're important. Now, why are they so important? Well, I'll give you a little bit of insight now, and we'll discuss it again later. Hydrogen bonds help to account for unique and important properties of water, and water is one of the most important inorganic compounds. Hydrogen bonds also help to provide the three-dimensional shape of proteins. As we'll find out, this is very critically important. And they also hold the two halves of the DNA molecule together. So water, proteins, and DNA are all heavily influenced by hydrogen bonds, making them very important bonds indeed. So again, this shows 5 water molecules. Again, the red sphere being the oxygen, the white spheres being the hydrogens, and this is showing a partial negative charge on the red sphere, the oxygen, and a partial positive on the hydrogen. And so you can see they line up, and all the water molecules tend to line up. And this has great implications indeed. We can see here that water is often very regularly organized because of the weak attractions of hydrogen bonds between them. So hydrogen bonding is critically important for water. And we'll explore this a little bit more in our next module, which will begin later. Thank you very much.